All right, welcome friends. It is time for your test review. So this is for chapter 3. So if you are not studying for chapter 3, you should probably find a new test review. All right, so with that said, let's get into it. All right, so this is question 1 is asking for the polynomial given, classify it by its fancy math term, find the leading term, find the leading coefficient, and find the degree. So the fancy math term, since this is a third degree equation, this is a cubic polynomial. This is a cubic polynomial. Cubic. Okay. Find the leading term. The leading term is the term that has the highest degree. So that is the 6x cubed. Regardless of the order that it's in, our leading term is 6x cubed. Our leading coefficient is the coefficient of that leading term. So in this case, our leading coefficient is 6. And then find the degree. The degree is the largest exponent that exists, and that exponent is a third degree equation. Okay? Simple as that. Just give me the stuff about the equation. Next, find the zeros of the given polynomial and state their multiplicities. So with zeros, anything that makes our f of x 0 is going to be a 0. So 0 equals x squared times 3x plus 2 times x minus 6. So any number that we can plug in for x that's going to make any of these things, that's going to make any of these terms 0 is going to be a thing. Is going to be one of our zeros. But if we have something times something times something, and it ends up equaling 0, one of those things has to equal 0. And we can say that x squared could be 0. We could say that 3x plus 2 could be 0. And we could say that x minus 6, that could also be 0. All right? X squared could be 0, so take the square root of both sides. Square root of 0 is still 0. So x could be 0. X could be, let's see, if we subtract 2 and divide by 3, we get 3x equals negative 2. Yeah, so x equals negative 2/3. And then we could also solve this guy for x, so we get x equals positive 6. So these are all of our zeros of our function. But we also need to state their multiplicities. Since this guy was squared right here, multiplicity, we had 2 places where we could plug in 0 for x and get our function to be 0. So this has a multiplicity of 2, which means it's going to touch and turn around. It's going to turn and go the other direction at x equals 0. Since this guy only is to the first power, because we don't see anything, so this guy has a multiplicity of 1. And then this last guy, same thing, has a multiplicity of 1. If it was to the 4th or 5th power, it'd have a multiplicity of 4 or 5, but it doesn't, so multiplicity of 1 it is. Okay? We're looking for the number of times that particular 0 shows up in our problem. On to the next question. Graph the polynomial function. Okay. Full disclosure, I love this problem. Problems like this, and this problem specifically, this is where I'm going to get most of your test, because there's so much that goes into this. I can break this down into multiple steps. Okay, so the first thing we always want, in order to graph the polynomial function, we always want to find that end behavior. Since it's an odd function, or since it's not an odd function, since it has an odd exponent, an odd degree, it is going to be, and the leading coefficient is positive. It's going to be down, and up is our end behavior. That's the first thing we always want to look for. Second, we want to see if we can factor this thing. If we factor out x squared, it's not going to be nice for us. It's not going to make the second parentheses, or make the parentheses match for either of them. So what we need to do is we need to use the rational roots theorem, or rational zeros theorem, or however you want to describe it. So first we need to use the rational roots theorem. And to do that, we take all the factors of the constant term, so plus or minus 6, comma, plus or minus 3, comma, plus or minus 2, comma, plus or minus 1. Order doesn't matter as long as you have them all listed, over all the factors of the leading coefficient, which is plus or minus 1. So all of our rational roots that we could use are plus or minus 6, plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1. Okay. Once we have our rational roots, we want to use Descartes' rule of signs. Descartes' rule of signs to find out how many of each different type of 0 we might have. So we could have some positives, we could have some negatives, and we could have some imaginaries. All right, so we make our table. We have, whoopsie daisies. Stop, touch, drag. There we go. All right. So since this is a cubic polynomial, we have 3 total solutions. Okay. We want to count our sign changes. First, we start with a positive. Then we go to a negative, so that's 1 sign change. Then we go to a positive, that's 2 sign changes, and positive, that's 2 sign changes. So we have 2 sign changes on the positive side. And then, if we find f of negative x, all of our odd signs are going to change. All of our odd exponents are going to change. So we're going to get negative x cubed. Negative 4x squared is not going to change. Minus x plus 6. So if we count here, we have negative, 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 and positive. So this is the 1 sign change that we have here. So we have one negative 0. And then, so if we have 2 positives, 1 negatives, that leaves us with 0 imaginary solutions. Now we could have, we can subtract 2 from up top, so we could have either 2 or 0, which gives us 2 possibilities. 1 is stuck the way it is, so that gives us just the 1 possibility. So 2 times 1 means we're going to need 2 columns. So we want to go through and list all the possibilities. Since this is always going to be 1, we can just fill that in. 2 could, if we subtract 2 and make those 2 imaginary solutions, we could have 0 positives and then have 2 imaginary solutions. So this is all the possibilities that we have for our outputs. Okay? Once we use Descartes' rule of signs, we then want to use this information to try and figure out what numbers we should use for synthetic division. So for synthetic division, I generally like to start with 1 and negative 1. But since we are guaranteed to have at least one, or exactly one negative solution, I'm going to go ahead and I'm going to start with negative 1 with synthetic division. So I'm going to use negative 1, and then 1 for x cubed, minus 4, 1, and 6. All right, let's check, make sure we don't need any placeholders. No, good, 3, 2, 1, 0. Awesome. So for synthetically dividing, we drop this guy down. 1, negative 1 times 1 is negative 1. 4 plus negative 1 is negative 5. 5 times negative 1 is 5. 1 plus 5 is 6. Negative 1 times 6 is negative 6. 6 and negative 6 is 0. So this guy right here is a solution. Yay! Awesome. So we found that x equals negative 1 is a solution. And then we're left with this quadratic equation. X squared minus 5x plus 6. If that equals 0, we need 2 numbers that multiply to be 6 that add to be negative 5. And there are 2 such numbers. X negative 2 and negative 3 equals 0. X minus 2 equals 0. X minus 3 equals 0. X equals 2. X equals 3. So let's take a look at Descartes' rule of signs. This guy right here, this guy is a negative number. He's the negative solution that we found using Descartes' rule of signs. And then our other 2 solutions are both positives, are both positive numbers. Okay? So hopefully that makes sense. We had 2 positive numbers. Ooh. We had 2 positives and 1 negative. And we have 0 imaginary solutions. We found all of them. Okay? So once we have found all of our zeros, then we want to make some intervals. So we start with negative infinity, go to negative 1. Then we start at negative 1 and go to positive 2. Then we start at positive 2 and go to 3. Then we start at 3 and go to infinity. So from here, we then want to pick some numbers on each of these intervals. I'm going to pick negative 2. I'm going to pick 1. I'm going to pick, let's see, 5 halves. And I'm going to pick the number 4. Okay? So from here, we start to make our table and we want to start graphing these things. Okay, so I'm going to go ahead. I'm just going to move this synthetic division for a second. Come with me, synthetic division. That looks like a good home for synthetic division. All right, so now we're going to make a table. X and Y. We already have some points filled out for us. We have -1, 0, we have 2, 0, and we have 3, 0. And then we pick the points -2, 1, 1, 5 halves, and 4. We also always want to make sure that we have x equals 0. Even if we didn't end up picking it on any of our intervals, we want to have x equals 0. So when we plug these guys in, we are going to get some values. I'm going to pause the video here for a second, and I'm going to calculate these things on my own so I don't waste time calculating things while you guys are watching. So I'm going to pause. I'll be back with some numbers. All right, welcome back. After doing some calculations, these are what I found to be the points. So once we have these points, we can go ahead and plot them. -1, 0. Let's see, 2, 0. 3, 0. Let's see, -2 is way down here at -20. 1 is at 4, so 1, 2, 3, 4. 0 is at 6. 6. 5 halves, which is right in between 2 and 3, is at 1.875, so we're like right here. And then 4 is at 10. I think this might be down here. Let me give me a second to recheck that. Yes, I did oops. 5 halves should have been -0.875. For some reason, I calculated the value for 3 halves. So once we have all these points, now we want to connect our dots and see if we can get a good picture. So let's use green again. So we're going to start over here on the left, and we're going to go up through this point, up around through 6, down through 4, get a little bitty bump down here, and then up we go. So we get that picture. That is the picture of our graph. If you graph this guy in your calculator, you'll see something really, really close. I really like this problem because you can actually do every single step of every single thing that we have done for this section. Okay? So expect to see something like this on your test tomorrow. Okay? With that said, let's move on to the next problem. Use the intermediate value theorem to determine, if possible, whether a 0 exists between 0 and -1. If it's not possible to determine using this method, state this. So we have our function g. So we're going to check g at 0 and -1. So g of 0 is, let's see, -2x cubed. So -2 times 0 cubed minus 3 times 0 plus 10. Well, this is going to be 0, 0 plus 10. So we're going to get g of 0 is 10. G of -1 is -2 times -1 cubed minus 3 times -1 plus 10. -2 times -1 is still -2, or excuse me, it's positive 2. Whoops. Minus 3 times -1, so that would be plus 3 plus 10. So that's going to be 15. So we have the points 0, 10 and -1, 15. Because these two y values are both on the same side of the x-axis, we can't say for certain whether there is a 0 between there. So this is indeterminate. There could be a 0 between the two, but we can't tell. Indeterminate because the y's have the same sign. If they were opposite signs, then we could say for certain, yes, there is a 0 between those two values. Okay? Moving on to number 5. So we need to use long division to divide these two, and then we want to express our answer like this. Okay, so let's do that. Long division. X to the 4th we need to have a placeholder for any x's that don't show up, any x to some exponent. So like right here, we don't have an x squared, so we need a placeholder for that. So minus 2x cubed plus 0x plus x minus 6. And we are dividing that thing by x plus 3. So we want to ask ourselves, x times what gives us x to the fourth? That is x cubed. X cubed times x gives us x to the fourth. X cubed times 3 gives us plus 3x. Now I'm going to change the signs. Change the sign. So negative 2x cubed plus negative 3x is negative 5x. We bring our 0 x's, or excuse me, negative 5x cubed, x cubed. Bring our 0 x's down. So we say, all right, what do we multiply x by to get to negative 5x cubed? We multiply it by negative 5x squared. So we get negative 5x cubed minus 15x squared. And now change the signs and add. So we get 15x squared. Bring down our just x. What do we multiply x by to get to 15x squared? Plus 15x. We get 15x squared plus 45x. Change the sign. And then we add, so that is negative 44x and then minus 6. Then we have, what do we multiply x by to get to negative 44x? We multiply it by negative 44. So negative 44 times x is negative 44x. Negative 44 times 3 is, let's see, it's 120 plus 12, that's 132. So negative 132. Change the signs and add. So we have, that becomes 0. 6, or negative 6 plus 132 is 126. And that is our remainder. Remainder 126. So we want to express p of x. So p of x equals divisor of x. So divisor is x plus 3 times quotient of x, which is x cubed minus 5x squared plus 15x minus 44. Plus our remainder, plus 126. So this is how we would like to report that answer. Okay? On to the next problem. So we want to use synthetic division to find the quotient and the remainder. Show your work. All right? Show your work is kind of a non-statement, right? You have to show your work all the time for everything. So, but we're given, this is a factor. Okay, this is a factor instead of an x equals a number. So we want to change the sign of this 2 to put that in our box. So we want to change that sign, becomes negative 2, goes in the box. Then we grab all the coefficients and put any placeholders that we might need. So we have 5, minus 3, 0, 1, and negative 2. So we are trying to find the quotient and the remainder. So we drop down the 5. Negative 2 times 5 is negative 10. Negative 3 plus negative 10 is negative 13. Negative 2 times negative 13 is positive 26. 0 plus 26 is 26. Negative 2 times 26 is negative 52. 1 plus negative 52 is negative 51. Negative 2 times negative 51 is positive 102. Plus negative 2 is 100. So our quotient, q of x, would be 5x cubed minus 13x squared plus 26x minus 51. And our remainder is 100. Those are our answers if we're trying to use synthetic division to do this problem. On to the next problem. Whoop. Hey, stay there. So we want to use synthetic division to find p of negative 3 for this function, p of x. So synthetic division, if we're finding a value, this is an actual x value. That guy right there is an actual x value. It's not a factor. So that goes straight into our box 3, and then we list all of our coefficients, again, including any placeholders as necessary. In this case, they are not, however, necessary. So 4, bring that down. 4, 3, now negative 3 times 4 is negative 12, plus 5 is negative 7. Negative 3 times negative 7 is positive 21, which then this is 19. Negative 3 times 19, let's see, that is 60 minus 3, so that is negative 57, plus 1 is negative 56. So p of negative 3 is negative 56. That is our solution for this guy. On to the next problem. We now want to use synthetic division to determine if 2 is a 0 of p of x. Answer with yes or no, show your work, and explain why. However, you don't have the function, the p of x, to do this, so I will grab it and put it right back. Okay, we're back. Our prodigal function has returned. Okay, this is our function that we're looking to see if 2 is a solution of, if 2 is a 0 of it. So, again, we're checking to see if 2 is a solution. I'm tired of green. Let's go red. 2. So then we grab our coefficients, again, using any zeros as necessary. So 1, or using any placeholder zeros as necessary. Negative 2, negative 13, and negative 10. In this case, we didn't need any placeholders because it went 3, 2, 1, and 0 on our exponents. So we drop this guy down. Becomes a 1. 2 times 1 is 2. Negative 2 plus 2 is 0. 0 times 2 is 0. Negative 13 times, or plus 0 is negative 13. 2 times negative 13 is negative 26. 10 plus negative 26 is negative 36. So because this guy, because the remainder is not 0, 2 is not, sorry about that, is not a 0 of p of x. Because our remainder is not 0, 2 is not a 0 of p of x. But we do have the point, 2 comma negative 2 comma negative 36. And if that's useful for us, we can use it. If not, we have it anyway. Better to have information and not need it than to need it and not have it. Okay, on to the next problem. Find a polynomial of degree 4 with negative 2 as a 0 of multiplicity 2, and 0 and 3 as zeros of multiplicity 1. So essentially they're saying our solutions are negative 2, because it happens twice, multiplicity 2, 0, and 3, both have multiplicity 1. So we need to make a polynomial of degree 4. This was our answer. So the step before that would be, well, x equals all of these things individually. X equals negative 2, x equals 0, x equals 3. And then we want to get we want to get 0 on one side of these equations by themselves. So x plus 2 equals 0, x plus 2 equals 0, x equals 0, x minus 3 equals 0. So from before this, we would then have had all these be multiplied together. So x plus 2 times x plus 2 times x minus 3. All right, so I'm going to multiply these two together, and I'm going to multiply these two together, because you can only multiply two things together at a time. So these all equal 0. So from here, we are then going to take x plus 2 times x plus 2. X times x is x squared. X times 2 is plus 2x. X times 2 is plus 2x. 2 times 2 is 4. So that's this guy, like one on the left. Then the one on the right, we're looking at x squared minus 3x. So now we need to multiply these two together. This 2x and this 2x combine to be 4x. Still equals 0. So we have x squared times x squared, which is x to the 4th. X squared times negative 3x is negative 3x squared. 4x times x squared is plus 4x squared. 4x times negative 3x is negative 12x squared. this would be, let's see, not 3x squared, not 4x squared. This would be negative 3x cubed. Sorry about that. 4x cubed. And then 4 times x squared is plus 4x squared. 4 times negative 3x is negative 12x. 0. So now we combine like terms, and we say, okay, x to the fourth, negative 3x cubed plus 4x cubed is plus x cubed. Negative 12 plus 4 is negative 8x squareds. And then minus 12x's equals 0. So there we have a polynomial of degree 4 that has negative 2 as a 0 of multiplicity 2, and 0 and 3's as zeros of multiplicity 1. This is your solution. This is your polynomial. Okay? We're working backwards when we're finding polynomials of degree blah. Okay? On to number 10. Suppose that a polynomial function of degree 5 has with rational coefficients 4, square root of 3, 7 minus 2i as zeros. Find the other zeros. So the other zeros are whenever we have a radical or an imaginary solution, we have to have the conjugate of it. So the other zeros would be the conjugate of square root of 3, which would be negative square root of 3, as well as the conjugate of 7 minus 2i, which would be 7 plus 2i. So these are the other zeros. And if it's degree 5, here we have 1 0, 2 zeros, 3 zeros, 4 zeros, 5 zeros. So we get our 5 solutions. Because it's degree 5, has to have 5 solutions. Okay? That's all there is to that. Just grab the other solutions that we need. On to the next problem. Next, we need to find a polynomial of lowest degree with rational coefficients and 5 and the square root of the negative square root of 7 as some of its zeros. So if we have the negative square root of 7, then we automatically need the square root of 7 as another solution. So our zeros are going to be 5, negative square root of 7, and square root of 7. Okay? So if you want to flip back, I believe it was to number 9. Yeah, number 9 that had another polynomial building. You can get all the details, like the super specifics. I'm going to jump ahead a little bit. So we're going to multiply x minus 5 times x minus the square root of 7 times x plus the square root of 7. Those are going to be equal to 0. I'm going to start with these two because they're conjugates. And multiplying conjugates together ends up with nice things. So we're going to have x minus 5 times, we have x times x, which is x squared, x times the square root of 7, which is plus x square roots of 7, minus x square roots of 7, because we have x times negative square root of 7, and then negative square root of 7 times positive square root of 7 is negative square root of 7 squared, which is 7. These two go away, and we're left with x squared minus 7 times x minus 5. So x times x squared gives us x cubed. X times negative 7 is negative 7x. Negative 5 times x squared is, is negative 5x squared. Sorry, got distracted by shiny things. Negative 5 times negative 7 is positive 35 equals 0. So if we reorganize this and make it look better, we have some function that is equal to x cubed minus 5x squared minus 7x. Sorry, that kind of looks like an 8. 5x squared minus 7x plus 35. This is our polynomial of lowest degree with coefficients 5 and negative square root of 7 as some of its zeros. Okay? Simple as that. So, next. Use the rational zeros theorem to list all possible rational zeros of p of x equals 5x cubed minus x squared plus 4x minus 2. If you flip back to the graphing one, I believe it was number 3, we go through everything, how to graph this, how we would graph this thing. Let's just find the rational zeros. So we need plus or minus all the factors of this guy. So plus or minus 1, comma, plus or minus 2. Then we also need positive and negative of our of our leading coefficient. So plus or minus 1, comma, plus or minus 5. So then we want to make all these into fractions. All right, so then this is going to become 1 over 1, so plus or minus 1, 2 over 1, plus or minus 2, 1 over 5, plus or minus 1/5, and 2 over 5, plus or minus 2/5. So these are all the possible rational zeros using that rational roots theorem, that rational zeros theorem. Okay? Just list all the possible solutions. Okay? Up next, for that polynomial p of x, we want to find all the zeros and express p of x as a product of linear factors. We worked through this one in class, but we'll talk through it again here. So for part A, we want to find possible solutions. We want to find possible solutions first because it doesn't factor nicely. It does not factor nicely, which is unfortunate. So we get, on our list of rational zeros, since our leading coefficient is 1, we're going to have all the factors of 12. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Those are all of our possible zeros. These are all of our possible zeros, so let's start checking them. All right, I'm going to start with 1, put it in the synthetic division box, 1. And then we have a 0 here, so we need a 0. We don't have any x cubes, so we need a placeholder for it. Then negative 9, 4, and 12. So we bring our 1 down. 1 times 1 is 1, 0 plus 1 is 1, 1 times 1 is 1, negative 9 plus 1 is negative 8, negative 8 times 1 is negative 8, 4 plus negative 8 is positive 4, or excuse me, is negative 4. 1 times negative 4 is negative 4. 12 plus negative 4 is that is positive 8. So 1 doesn't work. Negative 1. 1, 0, negative 9, 4, 12. Bring that down. 1, negative 1, negative 1. Oops. Negative 1. Okay, it's just going to live like that. So negative 1 times negative 1 is positive 1. This becomes negative 8. Negative 1 times negative 8 is 8. Just straight up 8. 4 plus 8 is 12. Negative 1 times 12 is negative 12. And then we get a 0. Okay? So this one does work. So solve x equals negative 1. So we need to check negative 1 again in case it has some multiplicity. So negative 1, we have 1, negative 1, negative 8, and 12. So we bring down the 1, negative 1 times 1 is negative 1, negative 1 and 1 is negative 2, positive 2, negative 6, 6, and 18. So negative 1 did not work again. So let's try positive 2 with our new solutions. 1, negative 8, and 12. Bring the 1 down. 1, 2 times 1 is 2. Negative 1 and 2 is 1. 2 times 1 is 2. Negative 8 and 2 is negative 6. This is negative 12, and we get a 0. So 2 works. 2 is a solution. Solve. So negative 1 comma 2. And now we have now we have a quadratic. X squared plus x minus 6 equals 0. So are there two numbers that multiply to be negative 6 that add to be 1? Yeah, absolutely. So if we have x plus 3 times x plus 2, that is the factored form of this guy. So we then have x equals negative 3 and x equals negative, nope, this is not positive 2, this is negative 2. And x equals 2. So 2 showed up again. So we have 1 comma 2, 2, and negative 3. So we have, or we can say that 1 multiplicity 1, negative 1 multiplicity 1 2 multiplicity of 2 and negative 3 multiplicity 1. So those are our solutions. So then for part B, we want to express p of x as a product of linear factors. So once we have those solutions, we can turn those solutions into factors, and we can say that p of x is equal to, parentheses, we turn those into factors, x plus 1 times x minus 2. Since we have 2 of them, we square it, times x plus 3. And this is part B. P of x expressed as a product of linear factors. Okay, on to the next one. Use Descartes' rule of signs to find out how many possible positive, real, negative real, and imaginary zeros could exist for the function as given. Okay, so we have some positive real solutions, some negative real solutions, and some imaginary solutions. I know your actual exam review gave directions a little bit differently, but this is what I'm going to be looking for. So we have some positive real solutions, some negative real solutions, some imaginary, and we have 5 total because we have a 5th degree function. Okay, we have a quintic function. So if we count our sign changes, we go from negative to negative, that's 0, negative to positive, there's 1, and positive to negative, there's another 1. So we have 2 positive solutions. Then if we f of negative x, all of our odd numbered exponents are going to change. The even ones will stay the same. So this is going to be 4x to the 5th minus 5x to the 4th plus 6x squared minus 10. So if we count our sign changes, positive to negative, there's 1. Negative to positive, there's another 1. Positive to negative, there's a third one. So we have, whoops, red's fine. So we have 3 negatives. And so if we have 2 positives, 3 negatives, that leaves us with 0 imaginaries. So if for positives, we could have 2 or 0. We want to be able to subtract. So we have 2 possible outcomes for positives. And then we could have 3 or 1. We could have 3 or 1, which leaves us with 2 possible outcomes for negatives. 2 times 2 is 4, so we're going to need 4 columns. So there's 2 columns, 3 columns, 4 columns, go away. So from here, let's go through all the permutations. I'm going to leave positives the same until we go through all the negatives. So we could have 3 negatives, or we could have 1 negative. If we have 1 negative, then we would have 2 imaginaries. Since we're out of negative solutions, now we change the positives. So we could have 0, we could have 3, we could have 2, or we could have 0, 1, and 4. These are all the possible outcomes that could exist for this particular function using that Descartes rule of signs. Okay, so this is useful for us when we are trying to solve some of these, when we're trying to graph some of these equations. Next, an object, and actually last, an object launched upward at a velocity of 4.9 meters per second from a height of 9.8 meters will have a height s of t equals negative 4.9 t squared plus 4.9 t plus 9.8, where s is in meters and t is in seconds. How long will it take for the object to hit the ground? So since s is the height in meters, the ground's height is 0. So 0 equals negative 4.9 t squared plus 4.9 t plus 9.8. Now, I would strongly advise for you to be able to factor this. Try to look to see what they have in common, if you can. And they do have negative 4.9 in common. So we're left with t squared minus t minus 2. All right. If you didn't notice that, then you could use the quadratic formula. But that quadratic formula is going to take you a lot longer than this is going to. So right now we have negative 4.9 plus this, or times this parentheses, equals 0. Something times something else equals 0. We know 4.9, negative 4.9 can't be it. So 0 has to be equal to t squared minus t minus 2. And do we have two numbers that multiply to be negative 2 that add to be negative 1? We absolutely do. T minus 2 times t plus 1 equals 0. Something times something else equals 0. We're not sure which one, so we have to set them both equal to 0. T minus 2 equals 0. T plus 1 equals 0. T minus 2, we solve that, we get t equals 2. T also could equal negative 1. However, since we're looking at how long, we're looking at time. Negative time doesn't make a ton of sense. So after 2 seconds, the object will hit the ground. 2 seconds. There we go, plural, multiple seconds. Okay, so that does it for your review. I hope some of this was helpful. You will be seeing all of this tomorrow. You'll be seeing all these various things tomorrow. So please, please, please study hard, study hard, study hard. And I will see you tomorrow. Have a great night, guys. Bye.